This is the screencast for section 8.2, example 5. So we're going to work with the indeterminate form infinity over infinity again. We're going to identify the indeterminate form and evaluate the limit using L'Hopital's rule, and of course support our answer graphically. So we have the limit as x approaches infinity of the natural log of x over 2 square root x. Okay, so first things first, plug in infinity and see what happens. I know it's weird to plug in infinity, but really conceptually think about what happens as the log of x approaches infinity. Those y values are going to approach infinity, and 2 times the square root of x as x approaches infinity, also the y values are going to approach infinity. So we get infinity over infinity. Well, that clues me into using L'Hopital's rule. So I'm going to take the limit as x approaches infinity of the derivative of natural log of x, which is 1 over x, over the derivative of 2 square root x, which is x to the now negative 1/2. So I'm going to simplify a little bit first. So I made that a square root. Instead of dividing fractions, multiplied by the reciprocal, simplify, and I get 1 over the square root of x. So now let's plug in infinity and see what happens. Well, 1 divided by the square root of infinity, well, the square root of x as x approaches infinity is also going to approach infinity. So 1 divided by a really large number is going to approach 0. Now the question is, does that graph really support our answer? Yeah, kind of. Our x values go out to 1,000. It's not obviously approaching 0. It might look more like it's approaching, I don't know, 0.2 or something. But if I made a window very large, I'm sure I would see that approach the x-axis, so y equals 0. The now try problem number 15 says identify the indeterminate form and evaluate the limit using L'Hopital's rule, and then of course support your answer graphically. So I have the limit as x approaches infinity of the natural log of x plus 1 over log base 2 of x. So first things first, let's plug in infinity, or at least conceptually think about what happens as x approaches infinity of both the numerator and denominator. Now, the natural log of x plus 1, which is just the natural log of x shifted left 1, as x approaches infinity is going to get infinitely large, and so is the log base 2 of x. So I have infinity over infinity as my indeterminate form. So now I can use L'Hopital's rule. The derivative of the natural log of x plus 1 is 1 over x plus 1. The derivative of log base 2 of x is 1 over x times the natural log of 2. It's not really much simplifying I can do here, but I am dividing 2 fractions, so instead I'll change that to multiplying by the reciprocal. And then I'll try plugging in infinity again. Now I have infinity times the natural log of 2, which is going to approach infinity, and then infinity plus 1. So I still have infinity over infinity. I got to use L'Hopital's rule again. So now I'm going to take the derivative of x times the natural log of 2. That's pretty easy. That's just the natural log of 2, the coefficient. It's like saying 3x. It's the natural log of 2x. Then the derivative of the denominator is 1. I don't even have an x to plug infinity into. I have my answer. My answer is the natural log of 2. Well, let's make sure. So I graphed in y1 the original function, and y2 the natural log of 2, and it sure does look like the function approaches that horizontal line, natural log of 2, as x approaches infinity.